All right, we're up and running now. By the time we get done with this section, hopefully we'll be able to conduct a matched pairs hypothesis test by comparing the means of two different populations. And of course, we are assuming that the samples are related to each other. They're pulled from both populations. Okay. All right, matched pairs samples. Matched pair samples or dependent samples are samples where the subjects are matched in or paired in some way. Here's an example. Suppose the heights of parents and children are being compared. So we have a population for parents and we have a population for their children. Okay. A pair might consist of a parent and a paired parent group and one of their children in the child group. And so because children are in the second population and related to parents that are like in the first population, these are called matched pairs here. And we like to keep our samples paired together. So like the parent that is selected from the parent group or population would be paired with their child selected from the child population or the child group, okay, in comparing some facet. Maybe like comparing their heights, okay. Another example would be a single subject, okay, is subjected to two different things. And those two different things are considered two different populations. For instance, a single group of subjects takes a test to test their reaction time. Then they are given a drug that should improve reaction times, and then they take the same test again. We keep the time to complete the first test paired with the time to complete the test after they're giving this reaction enhancement. We keep those paired. All right, and for that reason, we call it a matched paired sample here. Okay. Now, to compare the matched pairs, the difference of the values of the variable of interest for each pair is calculated. So the difference in height between parent and child, or the difference between reaction times before and after the drug, those would be the things that we would be concerned with as far as their differences are concerned. If the two groups are the same, these differences should on average equal to 0. So the null hypothesis would be saying that the mean differences between the populations is equal to 0, where mu sub d is the expected mean for the difference of the matched pairs. The alternative hypothesis then would take on one of our signs, okay, not equal to, greater than, or less than. You know, the nice thing about hypothesis testing is regardless of what we're testing for, and, you know, regardless of the situation, whether it's simple or complicated, you got to admit the alternative hypothesis always has these one of three symbols. Do you agree? Not equal to, greater than, or less than. That's really nice. That's one less thing to worry about. So our alternative hypothesis could say that the mean difference between matched pairs is not equal to 0. That'd be a two-tailed test. Or the mean difference between matched pairs is greater than 0. And in this case, ladies and gentlemen, because it's greater than 0, the order of subtraction would have significant meaning here, because this is a one-directional test, not a two-directional test like the two-tailed test is. So this is a right-tailed test. And a left-tailed test also, the order of subtraction and computing the differences between the matched pairs would be extremely important. Okay. All right. So these are what the hypotheses are going to look like when we conduct a matched pair hypothesis test. Okay. Now, the good news is that the test statistic is distributed according to a distribution that we've used in the past. It's not distributed according to some other weird continuous probability distribution that we have to get used to. It's distributed according to the t distribution, ladies and gentlemen, and we know all about the t distribution. We know how to compute critical t values using the inverse t function on the calculator or using our table in the back of our book. So that's good to know that there's nothing new with that. All right, now to calculate the test statistic manually requires more than one step, believe it or not. First, we have to calculate the difference D between the values for each of the matched pair data. So D is the difference between like the data pulled out of population 1 or sample 1 minus the observation pulled out of sample 2. And X sub 1 and X sub 2 are paired together. That's the important thing. Although these are pulled from two different populations, they're kept paired together. For instance, if X sub 1 is the height of, let's say, a father, and then X sub 2 would be like the height for like the child of that father. So we keep those paired together. Or if X sub 1 is the reaction time of a person after being subjected to some sort of test, and X sub 2 is the reaction time of the same person having taken the same test after having received a drug, in a reaction time enhancement drug, we would keep those paired, okay? So these differences are always the differences of paired observations, right? But what we would do is we would calculate all these differences as differences of these matched pairs, and then we would find the mean of those differences. We would compute D bar by adding all the differences together and dividing by the total number of differences. So that we have to take into account if we are going to be able to, compute our test statistic. Now, the standard deviation of the differences is computed by using this formula here. All right. But now listen, ladies and gentlemen, we don't have to go down to this level of complication. What we can do is we can like enter our sample 1 observations in list 1 and our sample 2 observations in list 2 in our calculator. And then list 3 can take on the differences between those values. And then we can use the 1var stats function to determine the mean of list 3 and the standard deviation of list 3. That will circumvent us from having to use this laborious formula to compute the standard deviation of our matched paired differences. All right. And also for computing the mean of those matched paired differences. So we'll take the bite out of that a little bit by using our TI-84 calculator. Now, the estimated standard error of all these differences, ladies and gentlemen, in other words, you could, pull out thousands or maybe millions of samples from each population and compute matched paired differences for each one of those paired differences, or paired observations rather. And all of those differences, okay, according to the central limit theorem, are approximately normally distributed. And so they form a sampling distribution, okay? Just like the differences between the sample means in the past formed a sampling distribution, or the differences between sample proportions formed a sampling distribution. Well, the differences of these matched paired observations also form a sampling distribution, and this would be its standard deviation. So this would be the standard error of that sampling distribution of the differences of all the matched paired observations chosen from the respective populations. Notice it requires the standard deviation of our matched paired differences divided by the square root of the number of ordered pairs, or the number of matched pairs. Then finally, we can compute our test statistic value, which is distributed according to the t distribution. It is the mean of our matched pair differences minus the mean of the differences under the null hypothesis, which is usually 0, but not always, divided by the standard error of the sampling distribution. To find our critical t-value, we're going to take it to the table or to our calculator with n-1 degrees of freedom, where n is the number of ordered pairs or matched pairs. Okay. These are the assumptions underlying the validity of such a hypothesis test. The sample or samples must be randomly chosen from the populations. But, ladies and gentlemen, we want to always keep these samples paired together that come from the populations. Meaning we always want our samples to be dependent for the situation here. That means we always make sure that they are paired sample results. If the sample size or sample sizes are less than 30, then in order for the sampling distribution to be normally distributed, we would require the parent populations to be normally distributed, or approximately normally distributed. Of course, if our sample size exceeds 30, we learned in the past that it doesn't matter if your parent population is normal or not. Your sampling distribution will always be normal. Okay, that stems from the central limit theorem. All right, here's a classic example to illustrate hypothesis testing for matched pairs. A dietitian wishes to see if a person's cholesterol levels will change if the diet is supplemented by a certain mineral. 6 randomly selected subjects had their cholesterol levels measured before, okay, notice measured before and after taking the mineral supplement. So, ladies and gentlemen, since we are using the same person and measuring their cholesterol levels before and after they take this mineral supplement, we keep those observations paired together. Okay, and because it's coming from the same person, we call that a dependent matched paired sample. All right. For instance, subject number 1, before they took this mineral supplement, their cholesterol level was 210. After they received the mineral supplement, their cholesterol level was measured again, and it dropped to 190. Subject number 2, before and after cholesterol levels. Subject number 3, before and after taking the mineral supplement, cholesterol levels, etc., etc. Okay. All right, and notice we keep these paired together. This is one ordered pair, if you will, or one matched pair. Here's another matched pair. All right, another matched pair, etc., etc. So we have 6 matched pairs in this investigation here. Can we conclude that the cholesterol level has changed at 10% level of significance? Assume that the variables are normally distributed. Now, ladies and gentlemen, since we're just testing to see if there is a change in the cholesterol levels with the before versus after taking the mineral supplement, would this be a 2-tailed test or 1-tailed test? What do you think? If we're just checking for difference versus indifference.
2-tail?
It's a 2-tailed test. That's correct. And therefore, our alternative hypothesis would have the not equal to symbol. Okay, where the mean differences is not equal to 0, meaning that there is a difference between the cholesterol levels of a subject before and after they take this mineral supplement, versus the alternative, the null hypothesis that says essentially there is no difference. All right, so these will be the hypotheses we'll be testing. It's a 2-tailed test. There's 6 subjects, so there will be 5 degrees of freedom, and we're testing at the 10% level of significance. The critical values would be positive and negative 2.015. And how did they get those? Well, you could use your inverse t function on your calculator, or you could go to your student t table and look up the values with 5 degrees of freedom. Notice this is a 10% level of significance divided equally between the lower and upper tail rejection regions. So the area to the left of our lower critical t-value will be 5%. 10% divided by 2, alpha divided by 2, so 0.05. Degrees of freedom is 5. And here we go. There would be your critical t-values, positive and negative 2.015. And you should also obtain that value from the table, the t-table in your appendix of your textbook. I understand there's at least one person that doesn't have the inverse t function on the calculator, but you should still be able to get those from the table. If you ever have any difficulty with that, let me know. All right, so now we know our critical t values. And you know my pet peeve with these PowerPoints is the author does not actually draw the do not reject regions. I always strongly recommend that you do this. It helps you to more conclusively understand what's going on here. Here's the upper tail critical T value. Here's the lower critical T value. Of course, this would be the negative 2.015 value here. And this one here would be the positive 2.015. All right, now the only thing that's lacking here is the test statistic. And so now we're going to show ourselves how to compute the test statistic in order to make a decision on these hypotheses here. Okay. All right. Okay, to compute the test statistic manually, ladies and gentlemen, first of all, we have to compute the differences that exist between the matched paired samples. Notice they're doing the order of subtraction of x sub 1 minus x sub 2, which is the cholesterol levels before the drug is taken versus after the mineral supplement drug is taken. So the difference in cholesterol levels for subject number 1 would be 20. Now, I don't know what the units are for the cholesterol levels. Trying to remember what they are here. It's so many micrograms, I believe, per volume of blood. I think that's what it is for cholesterol level. I can't remember the units. I think it was like microgram per milliliter or something of blood. I think those are the units, but they left the units off. All right, so you can see that we have our 6 differences. The differences being the cholesterol levels for each subject before the drug was taken versus after the drug was taken. Okay, notice subject 5, the cholesterol level actually increased a little bit between before taking the mineral supplement and after. And it increased also a little bit for subject 3, okay, but decreased for all the other ones. All right. Okay, now, ladies and gentlemen, you want to compute the mean of these differences and also the standard deviation. Now, look, you don't have to use this formula to do that. You don't have to use any of these formulas to do this stuff. We don't have to do any of this manually because here's what we could do. Just bring up your calculator. Okay. Bring up your calculator. And what we're going to do is look what you could do. You could even do it this way here. Okay. In list 1, you could type in the cholesterol levels before the mineral supplement was taken. So 210, 235, 208, 190, 172, 244. And then in list 2, you can record the cholesterol levels after the mineral supplement was taken. But you got to keep them paired. It's very important that the 210 cholesterol level before the drug was taken be paired with the 190 cholesterol level after the drug was taken for subject 1. It's critical that you keep these paired together. Otherwise, you don't have a matched paired design going on here. So 235 is paired with 170, subject number 2. Subject 3, 210 after taking the supplement, 188 for subject 4, 173 for subject 5, and 228 for subject 6. Now all you got to do is move your cursor to list 3, move your cursor up onto the name of list 3, and let the magic take place. All we got to do is say we want to take list 1, second 1 minus list 2, second 2. And list 3 is populated with the differences. Now all we have to do is go to 1var stat and find all the statistics for list 3. So second mode to quit, Stat, calculate 1var stat for list 3, second 3. And ladies and gentlemen, you have the mean of those differences, which is about 16.7. You have the standard deviation of those differences. Don't use lowercase sigma sub x, use s sub x. 25.4 is the standard deviation of all those differences. So you don't have to use this laborious formula. So you don't need a d squared row for your table here. You don't need that. You don't need any of that, okay? All you do is just enter this into list 1, enter these values into list 2, take the difference, this will be list 3, and then using 1var stats, you can find d bar and also your standard deviation of your differences. Does that make sense there? When you do the problem manually. So you don't have to use this formula here. Don't need that formula. You don't need this formula. Okay. All right, that'll speed things up. Okay, so now knowing the mean and the standard deviation of our differences, we should be able to compute our test statistic value. And using the aforementioned formula, the numbers get put in where they belong. 16.7 goes in for D bar, right? The standard deviation of the difference is 25.4 divided by the square root of the number of ordered pairs, which is 6. 1.610 is your standard deviation. Notice mu sub d is under the null assumption. Therefore, that's why it's 0. Because under the null hypothesis, mu sub d was equal to 0. See that? Where does 1.610 fall in relation to our reject, do not reject regions? Well, we can clearly see that 1.610 is less than 2.015 or upper critical t value. Therefore, it's tucked inside the do not reject region. And so therefore, ladies and gentlemen, we failed to reject the null hypothesis at 10%. We cannot reject this at 10%. And there's no way, if you cannot reject the null hypothesis at 10%, you certainly cannot reject it at 5% or 1%, because these rejection regions are going to shrink in size, and the critical t value is going to move even further away from your test statistic, tucking it more conclusively into the do not reject region. Do you agree? All right. Now, if you increase your level of significance from 10% up to maybe 25, 30%, yeah, this critical t value here in the upper tail might move far enough to the left and push the test statistic into the rejection region. The problem with that is you're increasing your chance of committing a type 1 error. Okay, of rejecting a null hypothesis that in fact may be true. So yeah, be careful. I probably would not reject the null hypothesis here, because it looks like that test statistic is rather far away from that critical upper tail critical t value there. And so, ladies and gentlemen, is the claim being supported by sample evidence? The answer is no. It does not appear that the mean difference between the two different situations is any different. In other words, it doesn't look like there's any difference between cholesterol levels before or after this particular drug or mineral supplement is taken. That's essentially what we would conclude in plain English. There does not appear to be a difference in cholesterol levels because of this mineral supplement. All righty. That makes sense there? That's a matched pairs hypothesis test there. And we could have also have conducted this test on our calculator directly. And we don't need any special function this time around, because it's just a t-test, ladies and gentlemen. That's all it is, an ordinary t-test. So we would go to stat, go to tests. We would select the t-test. Now we already have stats computed. So what's the under the null hypothesis? What's mu sub 0? That is 0, correct? That's actually mu sub d under the null hypothesis, which says mu sub d is equal to 0. The mean of this distribution is, excuse me, the sample mean is the mean of the differences, D bar, which is 16.666667. Interesting. That's weird. So, what's interesting here, ladies and gentlemen, is that because I entered my X sub 1 data in list 1 and X sub 2 data in list 2, when you do the t-test, your t-test is knows about that. In other words, knows that, if you want to conduct a matched pair test, things are already set up for you. Isn't that cool? It's amazing. I did not even specify list 1 and 2, but because I entered it into the calculator, I guess by default, this t-test looks at the two lists as being matched pairs. In which case, and that's what we want anyway. So this is pretty neat. Anyways, standard deviation is what it should be, 25.4. 6 ordered pairs. This is a two-tailed test. Calculate, and we would suspect the p-value to be large here, correct? Rather large. And it is. It's about 17%. So you'd have to drive alpha's value up to at least about 18% or higher before you could finally reject the null hypothesis and conclude there's a difference in cholesterol levels attributed to this mineral supplement. There's maybe too much risk there, ladies and gentlemen. I mean, you're starting to get up there with the risk in committing a type 1 error. So again, I would not reject the null hypothesis here. In other words, suppose that you were a drug company, okay? Well, you were like maybe the CEO of a drug company, and they came up with this new drug. Drug X, we'll call it. Would you want to go out there, ladies and gentlemen, and advertise Drug X as being a sure way of reducing your cholesterol levels? Would you think you'd want to do that here? Anybody?
No.
Yeah, I'd be a little leery about that because the hypothesis test is just not showing that to be true. There's risk involved in making a statement like that, okay? And I tell you, out there in the real world, if you spout off, saying, well, this will, help this condition go away in your body, when in fact, it's not really being, supported by formal statistical, inferential analysis. You got to be careful of that because, your company could get sued. And there's a lot of hungry lawyers out there, ladies and gentlemen, which is sitting around waiting to, sue a big old company like a pharmaceutical company that's, worth billions of dollars. All right. So, boy, you got to be careful. You got to make sure you do your homework first here. You got to make sure that you test it thoroughly with statistical analysis. And if there's any doubt, you need to go back to the drawing board, okay, and come up with a drug that is without a doubt conclusive, okay, with what it does before we actually start spouting off about what we hope it does. Okay, careful on that. So yeah, too much risk there. All right, so that's a classic example. Now, here's an interesting thing here. Suppose our researcher claimed that on average, taking the mineral raised cholesterol levels by 10 milligrams. Okay, so the units of the cholesterol levels are in milligrams. Then he or she could have used a different set of hypotheses. Do you agree? And the hypotheses would be these now. Notice mu sub d for the null hypothesis is not equal to 0 anymore. It's equal to what? 10 milligrams. Because now, ladies and gentlemen, we're testing to see if the cholesterol levels before and after taking this mineral supplement differ by more than 10 milligrams. And so your alternative hypothesis, notice, is mu sub d is greater than 10 milligrams. In other words, by taking this mineral supplement, has the cholesterol level increased by more than 10 milligrams? That's what we're testing here. Now, this will be a right-tailed test, notice, by the alternative statement. And suppose we want to test at 10%. We still have 5 degrees of freedom. We're still using the same data, all right? Nothing changes. Still the same before and after data set. All right. Now the critical T value, because our rejection region's in the upper tail of the size of 10%, the critical T value will be 1.476 now. And notice our test statistic changes a little bit because our mu sub D is not 0 anymore. It's 10. Because that is the null hypothesis purported mean difference between our matched pair observations, 10. So that's what changes there. And notice our test statistic is 0.6461. Well, I'll tell you what, let's draw a picture of our reject, do not reject region here underneath the student T distribution. And there's our upper tail rejection region, and its size is 10% of the area of the entire curve. It's 10%. The upper tail critical T value was found to be 1.476. And again, you can find that by using the inverse T function or your table in your book. Notice this test statistic is right about here. Do you agree? So it's far away from falling in the upper tail rejection region. And therefore, ladies and gentlemen, it looks like this is an extremely conclusive test for this particular test to say that no, it does not appear at all like, after having taken this mineral supplement, that cholesterol levels have increased by more than 10 milligrams. This is a very conclusive test. So there is hope for this drug, this mineral supplement. At least it does not increase, cholesterol levels more than 10 milligrams. That's a start. Do you agree? And we know that for a fact because this is an extremely conclusive test. There's no doubt whatsoever here. All right. But, maybe does it increase the cholesterol levels maybe by 5 milligrams or more than 5 milligrams or more than 2 milligrams? Ideally, we want this drug to reduce the cholesterol levels, not increase the cholesterol levels. But at least there's some hope here, a glimmer of hope that this drug is at least not pushing the levels more than 10 milligrams above the pre-drug measurement level. Okay. So there's some hope here, but I still think you got to go back to the drawing board and investigate this drug a little bit more here, right? And maybe tweak it, if you will, okay? So that it's more conclusive to maybe reduce cholesterol levels. All right. We can build confidence intervals for the mean difference between our matched pairs from our two different populations. And notice the confidence interval requires that we have the mean difference of our samples and our critical T value depending upon our level of significance or our level of confidence, if you will. And that's multiplied by the standard error of the sampling distribution here. So notice the lower endpoint subtracts off the margin of error from D bar, whereas it adds the margin of error to D bar for the upper endpoint of this confidence interval. And again, you still use n-1 degrees of freedom to find your critical T value. So what would be the 90% confidence interval? Ladies and gentlemen, did you get my email with regards to section, what was it, 9.3, I believe? When you construct the confidence intervals for the differences in the means that you need to construct your confidence intervals using the formula, the manual way, because that's the way Alex is computing them. Alex does not compute them according to your, what was it? What was the function we used 2 days ago? Anybody remember? It was the 2samp Z what? 2samp Z int function for the interval, confidence intervals in 9.3. No, wait. No. It was the 2samp what? T int function. Do you agree? In 9.3. So be careful in 9.3 when you're building a confidence interval, make sure you build them using the formula that's, in the PowerPoint presentation or in your textbook. Do not use the 2samp T int function. because Alex does not use that, because the degrees of freedom your calculator is computing is a heck of a lot different than the degrees of freedom that you should be computing, which would be the larger of n1 minus 1 or n2 minus 1. Okay. So be on guard for that. I sent an email out warning you of that. Okay. All right, ladies and gentlemen, check this out here. Notice that the lower and upper endpoint of this confidence interval, this 90% confidence interval, is a negative and a positive endpoint. That indicates that we're 90% confident that 0 is in this interval. Therefore, we're 90% confident in saying that essentially it looks like mu sub d is what? Equal to 0. Essentially, it's saying that there is no difference in cholesterol levels before and after you take this mineral supplement. And that adheres to our decision that we made when we conducted the hypothesis test back over here, that we were not able to reject the null hypothesis and conclude there was a difference. Okay. So your confidence interval decision has to be in line with your hypothesis test decision. Very important. All right, this is just going over the calculator, how we do this. It's just a t-test. That's all it is today. And, oh, let's see here. Let's see. Oh, for the confidence interval, it looks like they used the t-interval function here to build the confidence interval using your calculator. Let's go back and see if we can do that. So let's bring up our calculator. And unlike in section 9.3, we might be able to use our calculator to compute these confidence intervals here. So we'll go to stat tests, and it's not the t-test, but it would be the t-interval. The t-interval. We'll build this confidence interval here. Notice my stats are already known. So what's the mean? A D bar is 16.7. We can use that. The standard deviation is 25.4, excuse me. We're testing at, we're constructing a 90% confidence interval here, 0.90. And here's your confidence interval. Notice these values are in line, ladies and gentlemen, with what they got manually. So the good news here is, if you want to build a confidence interval for the mean difference between matched pairs, you can use your t-interval function. You don't have to do the confidence intervals manually like you do back in section 9.3. Okay? And so Alex should be in line with this too, as far as you using your calculator or building these manually, because they give you the same values. We're golden. We are golden. Okay? That makes sense there? All right, good. Well, let's go see if we can have some fun in our textbook and maybe apply some of this here. And these problems are going to be coming from section 9.4. That 9.4 is entitled Testing the Difference Between Two Means with Dependent Samples. You see, in 9.3, it was independent samples. All right. And you're always welcome to look down through, the examples in your textbook. That would be a wise thing to do. That only enhances your understanding of what's going on. It does take time, though. All right, so I would like us to try a problem here. So we have 9.4. Let's see if we can dive into problem number 2 here. Now, for problems 2 through 12, notice all this stuff they want you to come up with. State the hypotheses and identify the claim. Well, that's usually step 1 of the critical value method anyways, correct? B, find the critical value or the p-value method. That's step 2. And of course, always draw a picture of your reject, do not reject region or regions. Please always draw that picture. Compute the test statistic is usually step 3. Step 4 is make a technical decision. And then step 5, water it down so that like a 12-year-old could understand what you're talking about, okay? And the last step is a very important step because like I said, ladies and gentlemen, when you go, let's say you work for a company and they wanted you to do a test regarding a product that they're developing, and then they want you to basically go to a board meeting, and before all the CEOs and the department heads, they want you to basically state your report and your conclusions. Well, you need to realize that not all people understand statistics as in depth as you do, the researcher. And for that reason, you got to be careful about doing a snow job on them. And a snow job would be saying like, well, my sample evidence showed that I can reject the null hypothesis and only stand a 10% chance of committing a type 1 error. That would probably fly over most heads, and they would not even understand what you just said there. And for that reason, it's important to basically water it down, okay, to a point whereby even a layperson can understand and appreciate what the test is really concluding, okay, in plain English. All right, there's nothing wrong in being able to do that. In fact, that's a very valuable skill. Is to have somebody that knows the technical background and the technical details of a research project, and yet be able to, okay, formulate the results in plain, simple English that a layperson can understand. Not everybody can do that. Okay, some people are so technically oriented that they have a heck of a time trying to bring it down the level, ladies and gentlemen. You may have had an instructor like that. They're brilliant in their field, but sometimes they have a difficult time in bringing it down to your level whereby you can understand what they're even talking about. And I've had many professors over the years that were great, not only great theoreticians, okay, great in their field, but they were also great teachers too. I was blessed with a lot of great teachers in the past. There were some, however, that were great theoreticians, and I respected them deeply. But they had a hard time teaching the material. They had a hard time bringing it down to level, okay? And that's an art, that's a skill, okay? Being able to teach, all right? So that last step there, being able to summarize your conclusion in plain layman's terms, ladies and gentlemen, is pretty important, okay? In that way, anybody can appreciate what it is you did behind the scenes, albeit maybe very, very technical or very involved rocket science. Okay. All right. So we're going to try to do number 2 here. A random sample of non-English majors at a selected college was used in a study to see if the student retained more from reading a 19th century novel or by watching it in DVD form. Each student was assigned one novel to read and a different one to watch. One novel to read and a different one to watch. And then they were given a 100-point written quiz on each novel. The test results are shown. So, like, they were given a novel to read, and they were given a different novel to watch on DVD. You can see why they did not use the same novel on DVD that compared to the one that was read, because if you read the novel and then watched the DVD, you would have what? Reinforcement. Do you agree? And you would have biased results, because obviously after having read the novel, then watching the DVD, things are going to be confirmed with the DVD that you read in the book, and you would have a biased difference between the two. So that's why they had to read a novel and then watch a DVD involving a different novel. But because they're radically different techniques of, taking the information into the mind, they kept them paired, okay? The test results are shown at the 5% level can be concluded that the book scores are higher than the DVD scores. In other words, the claim says if you read the novel, okay, you're going to retain more information from having read a novel as opposed to having viewed a novel on DVD. We'll test that claim, ladies and gentlemen. In fact, I want you to test that claim. And I would like you to do this problem two ways. Critical value method, showing all 5 steps, and then the p-value method. And ladies and gentlemen, I want you to go the extra mile. I also want you to build a confidence interval in the end too, a T interval. Let's see if this all cooperates with each other when we get done with all these things. Now, keep in mind, when you do the critical value method, your test statistic, I want you to compute it manually using the formula for the test statistic. However, you can use your calculator to compute D bar and also the standard deviation of your differences. You do not have to use formulas to compute those things, okay? All right, I'll give you time to work, plenty of time to work on this. Problem number 2, interesting investigation. I'm curious myself to find out, ladies and gentlemen, if reading a novel enables you to retain the information better as opposed to if you watched it on DVD. Let's find out. Okay, classwork number 1, number 2.
How do we know which confidence level to test at?
You can test at 95% level of confidence because alpha's at 5%. So let's just go with 95%, okay? You know, 95% is a happy median between 90% and 99%. So when in doubt, always choose 95%, okay?
Thank you.
All right, now I put the scores in list one for the score on this retention quiz in list one for the people that for the reading of the novel, and the retention score for having viewed a novel on DVD were put in list two. I then took list one and subtracted off list two and stored those results in list three on my calculator. And therefore, Liz Almond, our claim is that we have a hunch to believe that reading a novel helps you to retain the information better than if you view a novel on DVD. If that's the case, then we would suspect L sub 1 minus L sub 2 to be greater than 0, correct? Which would say L sub 1 would be greater than L sub 2. The scores on a retention quiz would be higher if you read the novel versus if you watch it on DVD. So that formulated my alternative hypothesis. Mu sub d is greater than 0. That's my claim. The null hypothesis, of course, then would say the mean difference of the matched paired observations is 0. Testing at 5%. This is an upper tail test. So 5% of the area of the student t-distribution is found in the upper tail rejection region. Critical t-value was 1.94, whether you got it from the calculator or from the table. If you use it from if you get it from the table, you got to use n minus 1, which is 7 minus 1, 6 degrees of freedom. Okay, because there were 7 ordered pairs here. Now, by having constructed list 3 on my calculator using the 1 bar stats function, I was able to find the mean of those differences, d bar, and the standard deviation. On the calculator, d bar is x bar, and standard deviation of the differences is s sub x. So 6.3. Then I used those values and fed them into the test statistic formula here. D bar minus the mean of the differences under the null, which is 0, divided by the standard error of the sampling distribution here. 6.3 divided by the square root of the number of ordered pairs here, 7. Test statistic came out to be about 2.81. And you can see that since 2.81 is greater than 1.94, the upper tail rejection region cutoff value or critical t-value, our test statistic falls in the rejection region. And therefore, we will reject the null hypothesis. So in plain English, it appears, ladies and gentlemen, that if we read a novel, we tend to retain more of it as opposed to if we view the novel on DVD. And anybody could understand what I just said in plain English there. Okay, so very important to be able to, like I said, cut through the chase, cut through all the technical jargon, okay, because you understand it. But let's assume that somebody we're about to tell this to doesn't understand a thing about statistics, okay? I think they could at least appreciate what we say here, all right? So it's better to read a novel than view it on DVD if you want to, understand what the novel is all about. That's what this study looks like it's showing. And we only stand a 5% chance of committing a type 1 error and rejecting the null hypothesis and going with our claim. The p-value also confirms this because the p-value is 0.015 after conducting a t-test. And that's less than 5%. So it looks like we could reject this null hypothesis all the way down to 2%. Ladies and gentlemen, still be able to reject at 2%. We could not reject at 1%, but we could reject at 2%. And 2% is a very small risk of committing a type 1 error. So this is a very conclusive test here. The t interval, I built a 95% t interval, and sure enough, both endpoints of this interval are positive. And because both endpoints are positive, and my order of subtraction was L1 minus L2, that would indicate that L1 is greater than L2. In other words, the retention quiz scores for reading a novel are higher than the scores for viewing a novel on DVD. So The confidence interval cooperates with the p-value, cooperates with the critical value method. They're all in alignment with each other as far as the conclusion is concerned. And that's very important that that be the case. Did anybody confirm all this or get something like this?
Yep.
Yes.
All right. So that's a perfect example to illustrate a matched paired upper tail hypothesis test there. Okay. All right, that's a classic problem there. And again, the beauty is that you can use your t-interval function to build a confidence interval when you work on these with Alex. You don't have to use the manual method. And you can use the p-value method also. So that's a good thing. That speeds things up on Alex. All right, let's go down here. Number 6, PGA golf scores. I don't know if you golfed ever before, ladies and gentlemen. Maybe putt golf, or well, I don't know if that qualifies, but anyways, let's read this here. At a recent PGA tournament, the Honda Classic at Palm Beach Gardens, Florida, the following, that sounds so nice. Oh my gosh. The following scores were posted for 8 randomly selected golfers for 2 consecutive days. At the 5% level of significance, is there evidence of a difference in the mean scores for the 2 days? So we have golfer number 1, 2, 3, 4, 5, 6, 7, and 8, and we're comparing or keeping their scores matched together for the Thursday outing and the Friday outing for that same tournament. And we want to see if there's any difference, okay, between these scores for these 8 golfers and in being able to then project that onto the whole field, our population. Is there a difference in scores between Thursday and Friday? I have a question for you. What type of hypothesis test is this screaming for? One-tailed test or two-tailed test?
Two-tail.
Yeah, we're just trying to test for difference between the scores between Thursday and Friday. So I have a question for you. Does it matter what order of subtraction you use to find the differences between these matched pairs? The answer is absolutely not, because you're going to have a rejection region of equal size in the lower and the upper tail of the student t distribution. So it doesn't matter, ladies and gentlemen, which one you call 1 or 2. How do you label these samples? It's entirely up to you. I'll tell you what, so we're all on the same page. Why don't we maybe call, we'll call the Thursday scores we'll put those in list 1, and the Friday scores we'll put in L2. And then list 3 is going to take on the values of L1 minus L2. That way we'll be on the same page all together here, okay? All right, now, go ahead, conduct this the same way that we did the last problem. All 3 methods, ladies and gentlemen. Critical value method, p-value method, and building a t-interval, all right? Go ahead and do that one. Okay, so this is problem number 6. And we put the Thursday scores in list 1, the Friday scores in list 2, and list 3 took on the difference between the Thursday and the Friday scores. Specifically, the Thursday scores minus the Friday scores. The hypotheses we're testing would be for no difference versus difference between the scores on the 2 different days. Testing at 5%. Two-tailed test, that means the rejection regions are of size 2.5%. Using 7 degrees of freedom, my critical t-values were positive or negative and positive 2.36. D bar, which is 1 var stats of list 3's X bar is negative 1.75. There's a standard deviation of the differences, 2.05. Putting those in or substituting those into the test statistic formula, we come up with a test statistic about negative 2.41. Notice, ladies and gentlemen, it's close, but negative 2.41 is slightly smaller than our lower tail critical t-value, and therefore it does find itself in the lower tail rejection region. Not by much, but it does. Therefore, we will, at the 5% level of significance, reject the null hypothesis and conclude in plain English that there appears to be a difference between the scores on the 2 different days, Thursday and Friday. Sample evidence is showing that there is a difference between the Thursday and Friday scores. P-value was 0.047, which is very close to 5%, but being a little bit smaller than 5% still enables us to reject the null hypothesis. The t-interval is also very close with these endpoints, but notice both endpoints are negative, although this upper endpoint is very, very close to being 0. Do you agree? That's not far from 0. But nonetheless, it appears that since my order of subtraction was Thursday scores minus Friday scores, and both these endpoints are negative, that would suggest that it looks like the Thursday scores were maybe a little bit lower than the Friday scores. Okay, maybe not by much, but it does look like it. All right. And notice we can reject the null hypothesis at 5%. We could not reject the null hypothesis at 1%. But you got to ask yourself, is 5% of a ton of error or a ton of risk of committing to type 1 error? I mean, it's fairly low risk still. So I would probably lean towards saying, yeah, there does appear to be some difference between the scores between all players in the entire field. Okay, by just using this one sample, we can now extrapolate this to our population, these results here, and saying that, yeah, it looks like in general, scores are a little better on Friday as opposed to wait a second, ladies and gentlemen. Okay. Does anybody play golf? The real game. Anybody play the real game or watch golf ever? All right. Doesn't look like there's an overwhelming number of golf players out there. But ladies and gentlemen, I sit corrected in my conclusion here. No, there is a difference between the scores. Don't get me wrong. Everything that we've shown up here is 100% correct. Okay? Nothing wrong with what's going on here. But to say that the scores on Thursday are a little less than the scores on Friday, what is the better day for most golfers, Thursday or Friday?
Thursday.
Yeah, it is Thursday. Here's why. Let me go back to the data table here and show you. Okay. You see, ladies and gentlemen, these are called strokes. All right. The number of times you have to hit the ball to get it into the holes. Through a round of 18 holes of golf on a Thursday, golfer number one, had to, hit the ball 67 times to get the ball in all 18 holes and complete the course. The fewer number of strokes, okay, is the better score in golf. It's just the opposite of most games where the larger number is the better score. No, in golf, it's just the opposite. The lower the score in golf, the lower number of strokes, that means that's the better score. So what's happening here is because it looks like the number of strokes on Thursday is less than the number of strokes to complete the 18-hole course on Friday, it looks like golfers in general have a better day on Thursday than they do on Friday. All right, that's the way golf works. So if you shoot a 67, that's an amazing score because that means that in playing 18 holes of golf, you only had to, document 67 strokes to finish the course. Now, with like me, I'm not a professional golfer. For me to go out there and play 18 holes of golf, ladies and gentlemen, my score would be like about 150 or 170. Okay. 150, 170 strokes just to get, complete 18 holes of golf is a terrible score, but that's me. Okay. But professional golfers, normally shoot in the 60s and the low 70s for 18 holes of golf, which is really amazing. All right. So yeah, to have a 18-hole course day of 72 is not as good as if you only have 67 strokes for the whole day. All right. That's the way golf works. Okay, just one more problem, and let's see, it's 2:10, so we're running a little shy of time. And so, ladies and gentlemen, I would like you to do number 7, but you do not have to do it manually, okay? I just want you to conduct this test using your p-value method and also building a confidence interval for number 7. Now, let's just read it here and see if we can get a feel for what's going on. Psychologist has a 3-week program to raise the self-esteem of elementary school students. That's a good thing. A questionnaire was given to the students before and after the program. At the 10% level of significance, I don't know why they're testing at such high level of risk, but based on the scores of a random sample of 12 students, can it be concluded that the program increases the self-esteem scores of the students? So, ladies and gentlemen, what is our hope here? Is our hope that after the program, after having taken the self-esteem program, the scores are going to be higher or lower than before? What's our hope here for these kids? Our hope is that what? The self-esteem scores are going to be higher, correct? After these kids take this little program here. So let's let the before scores go in list 1. And let's let the after this taking the self-esteem program scores go in list 2. What is our hope here, ladies and gentlemen, if I do L1 minus L2? Do I want these differences to be greater than or less than 0 if we want this program to work for the kids? What do we want L1 minus L2 to be? Greater than 0 or less than 0 or equal to 0? What do you think? Well, if we want this self-esteem program to be doing its job in increasing the, the self-esteem of these students, these kids, we want this difference to be what? Less than 0. In other words, we want the self-esteem scores to be lower before they take this self-esteem course than after they take the self-esteem course. So I have a question for you. What kind of a test is going to be? Upper tail, lower tail, or two-tailed? What do you think?
Upper tail?
What's that?
Upper tail?
No, not upper tail. Look at this right here. Okay, this is our order of subtraction here. You see this? What's it going to be then? It's definitely gonna be a.
A lower tail.
It will be lower tail. So for the first time, we're gonna conduct a lower tail test. And look at this, I gave you a bonus here, a good jump start here. I already wrote down the hypotheses we're testing here. Ladies and gentlemen, I want you to use your calculator, use the t-test to conduct this hypothesis test and report the p-value, and also build a confidence interval, a 95% confidence interval, to see if those agree. This will be our last class work for today, okay? All right, so I entered all the data in the list one and list two. List three is going to be taking on the value of L1 minus L2. I'm gonna now go to one var stats for list three. Wait a minute, we don't need to do any of this here. What are we talking about here? All right. Anyways, ladies and gentlemen, we can just go do the test now. Stat, test, just a t-test here. We got our data in list one and two. Hold the show here. Wait a minute here. T-test. We want to conduct a t-test. Let's go to stat. Hold on a second. Stat. All right. No, we are going to use, okay, hold on a second. Looks like we have to use, in this case, I did put the data in list one and list two, but to do the t-test on this, we're going to need to know D bar. So we'll have to go to stat, calculate, one var stats for list three. Oh, list three. Okay, so that's D bar, which is negative 4.75. And S sub D is 7.723. Let's see if that imported that now into the t-test. So stat, test, t-test. And it did. We're good. We're golden. All right, so this is going to be a lower tail test. Oh, wait a minute. What's the sample size here? Was it 12? I believe it was it? Yeah, 12. All right, it's going to be a lower tail test. Calculate. And here we go. So the p-value is 0.03. So at 5%, we can reject the null hypothesis and conclude that, yeah, it looks like the scores, the self-esteem scores, were lower before taking the self-esteem course, ladies and gentlemen. That's what it looks like. It looks like the self-esteem course is having an impact on these kids and boosting their self-esteem. Let's build a confidence interval now, stat, test, go down, build a T interval. Everything should be imported into this one too. We don't have to re-import D bar and S sub D. It's all imported. 95% confidence interval. And there you go. Let's see here. Now, this is the 95% confidence interval here. Notice the lower end point is negative and the upper is positive, which means 0 is in here. So it doesn't look like the 95% confidence interval is reflecting that you know, there's a difference in these scores here. Let me build like a 90% confidence interval, see what that does here. Let's lower the level of confidence from 95% down to like 90%. Let me see what happens here. Well, what's going to happen, I think, is the confidence interval is going to then take on negative values for both the upper and the lower endpoint. Now, we could have some fun with this. For instance, let's increase the level of confidence. We can't go to 95%. How about 94%? Would we have difference in signs for like 94% level of confidence here? And notice we do, both endpoints are negative, which indicates we'd be 94% confident in saying that it does appear that the self-esteem scores before and are lower as opposed to the self-esteem scores after the children take this self-esteem boost class here. Okay. So yeah, it does look like there's some credibility to this course here. You know, we can't really say that at 95%, but you know, even at 95%, though our upper endpoint was positive, it was very, very, very close to zero. So I think that's still enough evidence to suggest that there is a difference. This course is making a difference, and it certainly isn't 94% in any lower level of confidence. All right. So that is it, ladies and gentlemen. I'm out of time. And so what we did is we conducted a hypothesis test today and built confidence intervals for the mean difference of matched paired data or dependent samples. And so I will stay on the line if you have any questions or comments. If not, have a great weekend, and we'll catch you next week, and hopefully make this final push to wrap this course up. All right, have a good day.